All right, so let's finish up these slides on qualifiers and quantifiers. Remember that qualifiers are like words that we use in English, like sometimes this happens, generally this is true. And we try to translate those kind of into quantifiers, which are mathematical things, logical things that let us specify something very, very nice and precisely, like logic helps us to do, right? Lots of math. Let's continue along those lines, because I want to, like, we learned how to specify, right? We learned how to specify things that are true, right? It is true that every non-empty list of numbers has a minimum, and here's how you can specify in math. Same with, what was the other one? Here's what it means that a list of numbers is sorted, so how to specify it. But how do you go and prove that your list is sorted using that specification? How do you prove that this is a true idea, right? It's just something that you can then go and prove true or false. That's what we've done. We've spelled it out in logic, but we haven't said, like, is it true yet? Okay. So that's going to be what we're going to do today. We're going to come full circle, and I'm going to show you that it's possible to write a program to prove that something is true, to prove a theorem. There's a very strong correspondence between code and logic, which is very fun to think about. All right? So yeah, I'm going to teach you, like, we're going to start with English again, an idea of something that we'd like to prove, translate it to math so that there's no ambiguity, and then bring code in, surprisingly, to help us prove that thing, right? So precisely. All right? So yeah, let's get there. The first thing I need to teach you, though, is a new term. All right? So this will come back later if you take more math classes or computer science classes, but it's the word predicate. All right? A predicate has nothing to do with the word predicate you know already from, like, sentences and stuff, right? Predicate is a special kind of proposition. All right? It's a proposition to start. Oops, let me fix my pen here. And we remember what proposition means. Yeah, that just means, like, some statement that's true or false, right? That's what a proposition is. Something that you can prove true or false. That's what a proposition is. So a predicate is that with some secret sauce. Something that is true or false. So that's what a proposition is. All right. And we're going to add some variables into it. So remember that a proposition is something like this. It's like, it's raining today. It's a statement, right? A sentence that can be proven true or false. Raining today. And this is totally a false statement, right? It's a false proposition right now, but maybe, I think I looked ahead on the weather, like Saturday, it's going to rain with like a 50% chance. So maybe that's going to be true. It's going to be a true proposition on Saturday, but definitely not today. All right, so that's a proposition. But a predicate is, take that, but add some variables, all right? So this is kind of what a predicate looks like. It's like a function almost. It's a function in math. You can think of. It's like, I'll use capital P. The predicate called P. It's going to vary in terms of some variable x, let's say. And let's define P of x to mean that x has a cat, all right? X has a cat. Does that make sense? And so x is a variable. Do you see how this sentence, this statement, is neither true nor false right now? Right? Because the answer is, it depends. Who is x? If you plug in me for x, I do have a cat. And so that's a true statement. But maybe one of you has a dog and not a cat, and therefore, it would be false for you. You see how, like, it depends on who x is. So that's what a proposition turned into a predicate looks like. Okay, you add a variable. And so if you'd like to, like, talk about true or falsiness with predicates, you have to apply it, kind of like a function call. It's like, this is how you say it. P of Lawton, right? P of my name, plug me in for x. Then it becomes like, Lawton has a cat. And that is that's a proposition, first of all, that you can prove true or false, and it is true for me, okay? But maybe it's false for you. Does that kind of make sense? That's what a proposition is all about. Depends on variables. It's not yet a predicate is like that. It depends on variables. It's not yet a proposition. You have to call the thing, call the function, I guess, all right? And so actually, the reason we're going here is because all of those quantified things that we were talking about, we had to introduce a variable all the time. So, like, for all L, there exists something called min index. Like, there's new names all over the place. And so all of these all of these quantifiers secretly have predicates baked inside of them, all right? So, like, when we said, for all x, P of x is true, or something like that. Or we said, for all x something. Like, it's something involving x, and so it could have been a predicate, is what I'm trying to say, all right? And so actually, do you see how you might read this for this definition of P? What would it mean for all of x, P of x, to say that? What's that equivalent to? How'd you say that in English, do you think? If this is what P of x means, x has a cat. What would it mean to say for all x, P of x is true? Well, for all means everybody, right? And we're trying to plug in people for that x. We're trying to plug in everybody for that x right now. See that? So this is going to mean everyone has a cat. It's trying to say that. Everyone has a cat. No matter the x, P of x is true for that person. Does that kind of make sense? I know we're going back to quantifiers and weird symbols, but that's what that would mean, right? If you were to say that for all x, P of x, and that's what P of x was. That would try to be claiming, right, that everyone has a cat. All right. We're good with that? Any questions about that before I talk about using these ideas? All right. So the goal is like this again, right? We got some English. We like to precisely say what we'd like to prove and then go off and prove it. All right. So I'll try to answer those questions today. All right. So here's a statement that I would like to prove. All right. There is a prime number that is greater than 50. Okay. This is a true statement. I think you can imagine, right? But let's try to build up the English for it and then eventually prove it. All right. So here's the goal. So let's say, all right, there is a prime number that is greater than 50. Which quantifier should we be using? Do we remember its name? We're going to translate this to math. What? Yeah, there's going to be a there exists, that backwards E, right? There is. So that'll eventually find its way in there. Good. All right. So let's say, all right, we got a number called x. Let's make a name for that prime number, right? We're claiming that there is one that's greater than 50. Let's call it x. What is true about x right now? All right. Well, it's greater than 50, right? And it's prime. Those are the two things we know that we're trying to claim about this number after we've given it a name, okay? So x must be greater than 50 and x is prime. That's fully describing this idea, yeah? And we're getting closer to more precision, more mathy stuff, okay? So x is greater than 50 and x is prime. Do you see how this is this is a predicate. This is something that's true, right? Could be proven true or false if you gave me an x. So it's a predicate. Depending on what x you give me, this may be true or it may be false. So here's a predicate popping up. And let's translate this further to math, like x is greater than 50. That's already math, right? X is prime is still English. So let's say we have like we have some other proposition that tells us if something is prime or not. Like we have something called prime. You plug in like 5 into the prime predicate, it says it's a way to prove that it's true. Prime of 5 is true. Let's say that prime it's some other predicate that proves primeness. 6 would be false, right? Because it's not prime. So let's use that kind of notation. This is getting closer to what we're looking for. So like this is what's true about x, right? It's greater than 50 and it's prime. Prime of x is true. Some other predicate. Okay. So that's kind of cool. It's just like it's predicates all the way down right now. We're using like function calls within function calls. Itself a predicate. Looks kind of like Python. All right. And now the secret is to like tack this back on at the front, right? We don't know what this x is. We're just claiming that there is one, at least one good one, right? And this is what's true about it. It's greater than 50 and it's prime. So as long as we're trying to prove this true, right? That there is some x for which this is true. So if we can just find that one good value of x that this will all work out for, then it works out, right? If we can find some x, there exists an x, right? Such that this is true for that x, all right? Then this must be the statement, right? Then the following statement is true, right? There exists an x, and then you read the comma as such that. That's just something you get used to in math. There exists an x such that, here's what's true about it. X is greater than 50 and it's prime, right? So there we go. We've just taken this idea, right, about some x, and we've like given meaning to that x. We've said like, okay, there is some. I'm claiming that there is some x for which that is true, all right? And now this is something you can go prove true or false, right? This was a predicate, like it depended on the x. This is now, like the quantifier has removed the predicate in a sense. This is now a statement, right? This is now a statement. It's a proposition. Something that you can prove true or false. And it's true, by the way. I'll show you how to prove that soon. Statement. All right, so it's a proposition. Which is really, really cool, all right? So does it make sense how this English, through all the ideas, became this logic? Any questions about how we did that transformation? Because now that's something that every mathematician can understand, and there's no ambiguity. All right, and that was the goal. This is now something we could prove true or false. Is there some x? Well, let's just go and find one, right? You give me one good one. I don't think 51 is a prime number, but maybe 53 or something. Like, there is one good one. We can shove it in there and show everybody, show the world that this is true. Okay, that's the goal. And so, like, this was a predicate before we quantified over it, and that's kind of something interesting, right? Here's the key for quantifiers. Every time you use a quantifier, you have to have a variable. It's like it's declaring a new variable, if you've heard that word before. Every quantifier creates a variable. You start talking about it. Here's an x. There exists an x. All right, let's talk about x now. Or go back to last time. There exists for every list L. Here's what's true about that list L. Every quantifier had a variable attached to it. It was creating a variable, all right? And that's a good way to, like, if you have a predicate, all right, something about some x's, you can translate it very quickly to a proposition by tacking a quantifier out in front. You're quantifying over the variable in the predicate, all right? I know these are a little complicated words, but that's the goal, all right? The more you stare at this, the more it will make sense. So now we've got something, right, that can be proven true or false. Now we got to figure out how to prove it, okay? So, like, do we all agree that we could prove that this statement is true, this proposition is true, if we could just find a prime number that's greater than 50, right? That would satisfy everything. Just like, okay, there's your x, that one, okay? Just point at it. So that's the goal, all right? And do you see how, like, you could write a program that could do this? That's coming full circle now, right? We could write a program that found that good number, and, like, that would prove our theorem, wouldn't it? That would prove our statement true. Isn't that cool? So, yeah, we can program this now. Let's talk about the algorithm, okay? So let's say we're trying to look for a prime number that's greater than 50, right? Let's try to figure this out. So, okay. Dun, dun, dun. Assume we have, like, an isPrime function, because we're going to keep on using that, right, to test if numbers are prime. And, like, it'll give back true if it is and false if it isn't. We ask for isPrime. Let's pretend we have this. We'll make it later. IsPrime of 42, that should give back, like, false, right? Because it's a multiple of 2 for sure. It's not a prime number. But can you imagine, like, all right, if I want to go searching for this number, well, let's start at 51, right? Let's start at 51 and keep checking, like, hey, was that prime? Was it prime yet? 51, was it prime? Shove it into this function. If it was true, we're done, right? Otherwise, keep on looking, all right? Add 1 to your, maybe it was like an I variable, I don't know. 52 is totally not prime, right? Because it's a multiple of 2, it's even. All right, then try 53. Plug that into isPrime. Like, the second you find one that it gives you back true for, right? Because you started at 51, it was bigger than 50. And then, because isPrime gave you back true, it was prime. You see that? So you can write a program to prove a theorem. Maybe 53 is still composite or whatever. You can keep on searching. But, like, just, like, keep a variable, right? Call it I or something. Start it at 51. Call isPrime on it. Keep on trucking if that's not prime yet. Keep on trucking if that's not prime yet. Eventually, I will find the next bigger number that's prime, okay? And so here's some code that might do this. So this is called pseudocode, by the way. It's not actually Python, but it's like English that looks like code. Computer scientists like to use this to, like, talk about an idea before you go and you code it up. It's like, here's like an Englishy idea of what we just said. It's like, all right, let's start iterating. Let's go through a bunch of numbers, let's say with a while loop in Python. Let's start first at 51. We'll set, like, our I variable at 51, all right? And then if I is prime, we'll keep calling this function, right? If I is prime, we'll stop the program. And there's a way to do that. It's called the quit function. Otherwise, just, like, keep on trucking. Add 1 to I, wrap around in your loop. See that? Add 1 to I, wrap around until I is prime. Are there any questions about that algorithm? See how it will eventually give us what we want? It will prove our statement here, our proposition, that there exists an x that's greater than 50 in prime. It's a lot of work, I know, for something so small, but, like, I'm planting the seeds of these ideas right now. We good enough with that? And so this is a very beautiful concept, honestly. You'll study this more if you take, like, a functional programming class at a 4-year college, or if you go into grad school for computer science or math. But programs can be themselves proofs. That's kind of what we're demonstrating right here. And there's a really, really cool I could just talk about forever, but it's well beyond the scope of this class. So so it's something that I enjoy. But yeah, programs can be proofs. That's kind of what I'm trying to show you here. And so let's write this program. Let's see that our statement is true, right? Prove it to ourselves. So, all right, let's write this code. I'm going to open up idle with a new folder for today. And what lecture are we today? We're lecture 21. So I'll make a new file and I'll save it in a lecture 21 folder. And what do I want to call this? Let's call it prime greater than 50. So we're going to write a Python program to prove this theorem. There exists quantified statement. All right. Let's make this smaller. So all right, we've got the game plan. We're ready. All right. Let's convert the pseudocode into real code. Not the pseudo means fake, right? Fake code into real Python code. So okay, what I want to do. All right. Let's assume that we have an isPrime function that we can go and call. What I'd like to do is start a variable, right? I at 51, because that's the first bigger whole number that's greater than 50, right? Only whole numbers can be prime. So start, and let's just do like a forever loop, while true, until the end of time, until I find one. Keep searching forever if there isn't one. Who knows? While true, like I've got a value of I right now, right? Let's check it. Check if I is prime. And if it is, we should stop, right? If it is, print it out and stop the program. We don't need to keep on going forever. We found a good value. That can be our x, right? From the previous slide. And otherwise, right? Otherwise, if that wasn't true, if it wasn't prime yet, increment I, right? If it wasn't true for 51, try 52 next. Increment I to the next number. So that we can check the next value. And you could be smarter about this. Like you could know like that 52 is never going to be prime. So like add 2 to I instead of 1 every time. Like, that could be better. But I'll just do it very naively. So there's that. And let's code up all these comments. So let's check if I is prime. All right. So if is prime of I gives back true. That's equal to true, right? That means it was. Does that make sense? Checking that? It means it was true. Print it out and stuff. Right? This is kind of redundant. I'll fix that in a second. But like, all right, if it is prime, right? If it gives back true, then let's print out my current value of I. That's the good one, right? Print I. And then we'll stop the program, and it's called quit. That stops the program. It's a function call baked into Python. It'll just stop your program, even if it's a runaway infinite loop. Quit will stop it. And then otherwise, right? Otherwise means in or else, right? Else. So we could add an else, but honestly, like if we went to this one, the program would have been stopped. So technically, I don't even need an else, right? If we're still going, if the program is not stopped yet, we're gonna come out to here. Otherwise, increment I equals I plus 1. So we wrap back around, right? This is never gonna stop unless we quit and keep trying. All right, so that's gonna be the code. Does that make sense? We'll be searching for the next prime number, and that will be I, and we will print out probably 53, right? I think that's the next prime number, if I remember right. But this code actually is a little bit inefficient, or not inefficient, it's kind of redundant. So remember that an if statement is going to check its condition and like run the body if it's true, if like it results in true. And so like, honestly, I don't really need this equal true, because just like read it like this: if is prime of I is true, do this stuff, right? Because this will get replaced with true if it was true, and true things run the bodies. Does that make sense? That's exactly equivalent to checking if it was true. Just like saying is prime of I. If is prime of I gives back true, do this, right? So that's that. And that will work if we had an is prime function. Sadly, we don't get one of those in the library, so let me very quickly, you can look away if you'd like, because I haven't taught you how to make, let's see. I haven't taught you how to make functions in Python yet, have I? No. So I'm going to have to make an isPrime function, so you can look away if you're scared of this, but I'm going to show you, right? I'm going to show you the secret. So let's learn how to make an isPrime function. Don't worry too much about the implementation and the math involved, but like the scaffolding you will eventually learn. All right, so let's write up here our game plan. Like, how do you check if a number is prime? All right, So like we give a number like 51 or something. Like that's the first one we try. How do we know that like that's not prime, right? It's not prime because it's divisible by 3. 5 plus 1 is a multiple of 3, right? So how do we like check all this stuff? So what we need to do, right, to check that a number is prime, you just have to keep on dividing it essentially. So here's the secret that we'll translate into code. So a number, call it n, all right? A number n, it's hard to write small. A number n is prime when you try to divide it by every number smaller than it, starting at 2, right? When like 2 and 3, all the way to even n minus 1. You could technically stop early, but let's go up to n minus 1. Don't like divide in cleanly, right? None of those are multiples, right? Don't divide. Let's say divide cleanly into. So that kind of makes sense. Like, all right, 7 is prime because like you try 2, try 3, try 4, try 5, try 6. None of those divide into 7 cleanly. That means it's prime. It's got nothing that can split it up perfectly. That's what it means to be a prime number. There's no factors, right? So you're kind of searching for a factor. That's kind of one way to check if a number is prime. So like if n is 51, you're going to keep on trucking, right? You're going to start at 2, like check, hey, is 2 divisible? Or does 2 divide 51? Then does 3 divide 51? And keep on trying. Go all the way to 50 if you need to, if it's prime. But I think we're going to stop at 3 probably, right? Because that's going to notice that it's definitely composite, or it's a multiple of 3 at least. And the way that you check this, how do you check if something divides cleanly into something else? It's the remainder operation, all right? Remember that one? That's the percent sign. So like here's what we got to do, like 51% sign. It's called modulus, 51 mod 2 for short. Doing this, that's going to give back. Here, I'll do it on the rectal, 51 mod 2. It's going to divide by 2 and give back the remainder. And that isn't 0, right? So 2 does not divide in cleanly. So it's not a multiple of 2. That's what you can conclude. That's 1. But 51 mod 3 will definitely give back 0 because it's going to go in cleanly when you divide by 3. So there's going to be nothing left over. And if you notice that ever, that means it wasn't prime. Does that kind of make sense? That's going to be the secret. And so if you try all the numbers and none of them work, they all go in and like there's something other than 0. Like they don't go in cleanly, none of them. Then that means the number was prime because nothing worked. Okay, so that's the secret. And let me very quickly translate that to code. All right, so you don't have to understand this. Don't worry, I'm just making it as prime function. But this is good learning ahead for next time when I do teach this. All right, so to make a function called is prime, you say def. Def is prime, and then you give the thing that you're getting. Like we're going to call the thing that we're being given n, let's say. And then what we do is, all right, we've been given an n value, and it's our job to give back true or false. Was that n prime or not? So what we got to do is try to divide by 2, by 3, all the way to n minus 1. And I will teach us how to write functions very slowly soon, but this is just me going fast, so we can do this before the end of class. So let's say that, let's use a j variable instead of an I variable, because I want to iterate again. Let's start our iteration at 2, go all the way up to n minus 1 if we have to, right? So while j is less than or equal to n minus 1, whatever that was, like 50, keep on trying this, right? Try to divide n by j, starts at 2, try to divide like 51 by 2, 51 by 3, whatever j is right now. And like if it worked, we're good, all right? So if n divided by j, get the remainder, gives back 0, that means j was a multiple of n. All right, that's this example. 51 mod 3 gives back 0. 51 was a multiple of 3. It's not prime. All right? So j divided n, divided cleanly into n. So that means j is a factor of n, and prime numbers don't have factors. So we can give back immediately. Nope, false. This number is not prime. You say return for that. Otherwise, keep on trucking. Keep on trying more numbers. J equals j plus 1. All right? And then if this loop ever ends, that means you never gave back false, and you tried all the numbers. So if we get here, there were no factors. That means it's prime. Nothing went in cleanly. It's a prime number. Return true. All right? And so that's the secret. That is prime. Don't worry. if that didn't make any sense at all, I will go very slowly and talk about how to like make functions, probably, if not next time, the time after that. But look at it. I ran it as just a very long-winded program that prints 53, right? Because remember our goal. We're looking for the first number bigger than 51. That was prime. 51 didn't cut it. 52 didn't cut it, but 53. And then it quit. And it's like, do you want to stop the program? Yes. And then it goes away. But that's the secret. It did it. It worked. 53. Beautiful. Are there any questions about that? So we've come full circle now. We've made a precise specification for what we wanted, right? This is what we wanted. We just proved this, right? And we used code to do it, right? When we did that. This is the relevant part. Are there any questions about that process? It's a long-winded example, but it's a cool idea that you can come full circle like that just by being a programmer, I think. All right, so let's see here. I got a question for you in just a second, but let's break it down first. Here's another thing that we can prove. We can specify using quantifiers and then prove using code. All right, so let's prove that for all integers, call them n, between 0 and 100, the square root of n is less than or equal to 10. And that's a true statement, right? If you could prove that, if you knew how, like that's a true statement because the square root graph would look like this for all these numbers between 0 and 100, right? It grows like this, monotonically increasing, we say, and like it's exactly 10 at 100, isn't it? It's exactly 10, and so it's never going to get any bigger. It's always less than or equal to between 0 and 100, yeah. So that's something we can go and prove now. Let's try it. We want to convert it to better looking English, like you have the word for all, right? We can totally translate that into a quantifier. But also we've got some side conditions, like this must be true about n in order for this to be true for it. Like don't let n get bigger than 100. If so, like this does not apply anymore. So it's actually secretly an if-then statement. All right, so here's the secret. You kind of see how those are going to fall from there. So like we want to talk about numbers that are between 0 and 100. This is true about them. It's like, and only if that's the case, right? Only if we're talking about an n between 0 and 100. Then we're claiming this about that n. We're not claiming anything about any bigger or smaller n values. Does that kind of make sense? That's more mathy looking English. If n is greater than 0 and n is less than 100, then this is true about those kinds of n. All right? Their square root is less than or equal to 10. And that is looking better because that's another logical symbol, right? That's our if-then. That's our implication. Okay? So does that step make sense? From there to there? The top down to there? Questions about that? If that's true, this is picking out the range, right? If this is true, all right, here's something I'm claiming about those number n's. Okay, cool. And then we want to go even further, right? Convert it to complete math. So like, all right, get rid of these statements, do this kind of stuff, the and also, right? So this is the same thing still, right? This is our if then. You read it as if then. If this is true, then this is true. So if n is greater than 0 and n is less than 100, less than or equal to, that's picking out this range of numbers, then this is true. I'm claiming that this is true about those n's. Their square root is less than or equal to 10, right? And again, I have a statement that's neither true nor false right now, do I? Right? Because n could be anything. N could be 200 right now, for all I know. It's false if that's true, right? If it's false, or I guess it's vacuously true, we say. But like n could be 200, and that might throw things off. But it could be 0 and 100 either. It could be between there as well. So anything that's not yet a proposition, it's not yet something we can prove true or false. We like replace the n. That's called a predicate, right? So that's a predicate. And yeah, if we would like to translate it into something that we can prove, we're going to add in a quantifier, and that's the last thing that we've not yet done. Okay, so add in that quantifier at the final stage to create a proposition out of the predicate. So for every n, for all n values, if this is true, right, for every number n, if n is between 0 and 100, it's greater than or equal to 0 and it's less than or equal to 100, then its square root is less than or equal to 10, right? So again, that's the full story. That's the big step from here all the way down to this. And now this is a proposition that we can go and prove true because it is a true statement. All right? Again, it takes a while to get there, but that's the secret. We went a little faster this time. Do yell at me if you have questions about this. Does it make enough sense? Kind of see the process? So yeah, you'll get even better at this if you take a future computer science class, but this is like the taste of it that I want to give you in this class. And so again, like sometimes it's hard to look at this and understand what it's saying, so like I like to add some English as well. It's like here's exactly what this means when you come back and study later, right? For all n, right? We're talking about n as a number, right? For all numbers n, if this is true about n, if n is greater than or equal to 0 and n is less than or equal to 100, that's the part that's picking out the range that I care about. Then here's what I'm trying to prove for those particular n values. Then its square root is less than or equal to 10. Right? So that's how you would go back to English. Super precise English now. But yeah, this is something that everybody can understand, every mathematician, and you guys count now. And yeah, you can go and prove it true or false. All right? Are there any questions about that before I ask you to try that? So please help each other. Get close to one another if you would like. But I want to give you this code because it's going to be a similar idea, right? If you think about it, I am trying to, right, we're trying to find a number, or we're trying to prove that every number within a range, something is correct about it, something is true about it, right? And so, like, you're going to have to iterate again. You're going to have to try out a bunch of numbers, right? Because they're all supposed to do something, right? Something's supposed to be true about them. And, yeah, see if you can, using these ideas, right? I want to prove that every number within this range, its square root is less than or equal to 10, right? That would prove my theorem. Can you see how you might use a loop to do that kind of check? Think about it, and I want to give you some time to try it. You're going to need square root, and that's in the math library. Import math, and it's going to be math.squareroot, math.sqrt, like of 2 or whatever. And that's how you use the square root function, all right? Because you're going to have to keep checking, right? You got a lot of numbers that you got to make sure this works for, don't you? Those are my hints. All right, are there any questions about how you might attempt this? So using my iteration as an example, see if you can prove this. Because it is a true statement. See if you can prove it in code. I'll give you some time, plenty of time to think about it. And then I'll do it too. So I'll give you like, I don't know, a 6-minute head start, let's say. And feel free to like make some game plans with each other, get close. I'd be happy to help as well if you have questions. I don't think so, actually. Let me look ahead. Yeah, no, that's going to be the next programming lecture is 4 minutes. Yeah, exactly. And just like range, the range function. We'll talk about that next time. Yeah, give this a try. That's how we learn. Come up with a game plan with each other, and yeah, I can help answer questions if you have any. So I'll have to put these back when I finish. But yeah, remember that this code was like looking for one good value, and that was a there exists proof. We got a for all this time. How do you iterate? Which numbers do you have to go through? That'd be the first question to think about. What do you want to check about them? All right, I'll show you my answer in 15 seconds. All right, did any questions come up as we were trying this that wouldn't be solved or answered by me showing the answer? What was the pseudocode? What was what was the algorithm? What do you guys think? Like, what's going to prove this? What do we got to do? Can anybody say it in English? To show that that's true, what must be put in code? Good, yeah. Awesome, yeah. Very good. Does that make sense to everybody? So you're going to try them all. So we're saying that they're all true for every n value within that range. So we have to, we got to check them all because maybe one's a bad one. We have to check each one because we're not sure, which one's going to be the issue. And hopefully none of them will be, right? So here's the secret. Very good. So yeah, this is kind of like the pseudocode that I would think of in my mind. Let's loop through every number, call it n between 0 and 100. All right, start n at 0, make it be, and then keep on checking its square root, right? Because we got to make sure that every number within that range, its square root is less than or equal to 10, right? Check the square root of 0, which is 0, right? Make sure that's less than or equal to 10. Check, right? Do 1. Try its square root, right? Make n 1. Okay, does that make sense? And then keep on trying them. We want to go through all these numbers and try their square roots. Square root of 2, make sure that's less than or equal to 10, all the way up to 100, right? Make sure that its square root is less than or equal to 10. Okay, so this is kind of the code to do that. Loop through every number between 0 and 100, and if you ever see, right, if you ever see one that's bigger than 10, that means that's the opposite of this, right? If you ever find a number within that range that's square root is bigger, then we can just give up, right? That one's not a good one. They were supposed to all work, right? It was supposed to be for all. We found a bad one, a counter example, we say, and so we can stop and print false. Otherwise, if we get through the entire loop without ever complaining, then we can just print true, the statement was true, our theorem was true. Okay, does that make sense? Keep on checking, making sure they're all less than or equal to 100, because you could do that way or the opposite way. It makes kind of more sense to me. If you ever find a bad one, that means it was bigger than 10, not less than or equal to. Okay, so let's try to code that. Let me show you how I might write it. This one, at least, square root is made for us by the library people. Thank you, math library people. So I'll call this square root proof.py. And I'll import math so I can use the math.square root. And let's make it happen. All right, so let's use the number n this time. Why not? So n starts at 0, right? It's going to go up to 100. It's while n is less than or equal to 100, do stuff, and then increment n. It's this is now a loop that's ranging from n being 0 all the way to n being 100. 0, 1, 2, all the way to 100. And what do I want to do with each value, right? I want to check them. Make sure that every square root is within the right range. So if it's ever within the wrong range, if math.square root of n is ever greater than 10, then that's not a good thing. That was not what was supposed to happen, so we'll print false, exclamation point, because our theorem now is false. Now we'll quit out of the loop. This did not work, okay? But you see how if you get through all the numbers, you will never get here and you'll never stop, right? Because quit stops the program. So if you ever get past this entire loop and it never stops the program, that means every number worked. Every number was a good number. Every number's square root was less than or equal to 10. And so if we ever get down here, the statement must have been true, the proposition. Cool, and capital true, right? So, all right, what does that mean for us? Well, we got to shout it out to the world. Tell our program to inform the user that, hey, it worked out. It was true. Okay? So that's going to be the code, and you can have it print out more. You can print out which value of n it was trying, if you'd like. But this is just going to be a program that's either going to print false or true. Does that make sense? It'll print false if it ever finds a bad number. That's between 0 and 100, because that's the way we're ranging. That's greater than 10 for its square root. But if we ever get passed all that, we try them all and none of them were bad, then all of them were good. That's how you can think of it. And so this print's true right now. And that is a program that proves, what was it? Proves this, right? This theorem. For all numbers n between 0 and 100, the square root of n is less than or equal to 10, aka this in math. We again have come full circle. Are there any questions about how this code, where is it? This code proves that to be true. It's a very powerful idea. All right, so let's see here. Yeah, there's just a very strong correspondence between code and proofs that you may explore later in the future. But let's see. Let's have an example of this code saying something that's wrong. Let's try to prove something that's false. Let's try to prove that for every number n between 0 and 101, the square root of n is less than or equal to 10, right? So let's try this one with our code, because that's not going to be true, is it? It'll show us. It'll tell us that no, we found a bad one. It's not working. Like, how do we change this to like try to prove that theorem? It's like, all right, just change the way you arrange and go up to 101 this time. And as you know, it's going to print false because once it hits 101, that's bigger than 10, right? The square root of 101 is slightly bigger than 10. And so, like, we were trying to claim that they're all less than or equal to 10. Uh-oh, we found a bad one, false. And so, again, the program caught it and showed us that our theorem was false. Isn't that cool? I love that. So, yeah, this is some good examples of looping as well to study, all right? So, yeah, it's kind of a philosophical day, even though it's a little bit of code as well. Logic is philosophical, I would say. Yeah, so any questions about this example? Does it kind of make sense how we would do it? Once you wrap your mind around it, it's pretty cool, all right? So the moral of this story, where I'm going with this, is like logic and computer science, they are interconnected. Like originally computer science was an offshoot of mathematics, and this is really showing right now, okay? So that's the goal. I just want you to go back to the roots and take advantage of all the things that all the nice mathematicians have proven for us, all right? So if you use both, you think logically, you try to prove that your programs are correct, like you're going to have that correctness idea in the back of your mind, right? And that will help you write correct programs the first time, maybe. And also, like, argue why the ones that you've written are right, or maybe notice an issue faster and argue. Like, try to reason with yourself, like, where's the problem? Just like thinking logically and trying to prove to yourself that it's working will guide you to the answer one way or another, even if it's wrong currently. All right, so that's where I'm going with that, and I think it's a fun little idea. Okay, yeah, so that's, I think, what I wanted to say about quantifiers. Any last questions about these things that we talked about today, either of the examples? There were two big ones together, weren't there? All right, so I'll give you all this code to take a look at, and yeah, the very last thing I want to do, give you plenty of time to study and work on your essay. I want to give you your new essay. All right, so you got one due this week, and I want to give you the next one. It'll be take 2 weeks to do it, plenty of time, and it's shorter than the one that's out right now. All right, so this will be a 750-word essay, and here is your prompt. So after you get the current one in, you can start this one. And here's the setup. This is a very philosophical question that I'm trying to ask you here. So, like, go and pick your favorite painting, first of all. If you don't have one, go find one. Right? Go find a painting that someone has made sometime before 1900. All right? That's going to be my cutoff. So, like, go to one of the earlier eras. Go pick your favorite painting. If you don't have one, there are plenty of websites to help you find one. All right? So that painting was painted by an artist by hand. All right? So that's the start. Now assume, here's what I want you to do. Assume that that artist who made that really nice looking painting way before Photoshop existed, right? Assume that they were alive today and they made that same exact painting on a computer, right? Using today's technology, like they were using a drawing tablet like I am in class. They were using Photoshop, which it's got some virtual brushes, but it's not like they're slathering paint on an actual canvas. It's virtual paint, virtual canvases, okay? So imagine that that artist was alive today, made that beautiful painting that you love so much, using digital techniques, right? My question is, would that painting that you like so much still seem as beautiful to you? Would it be more beautiful, less beautiful? I don't know. Tell me why or why not. All right, this is just an analysis kind of essay. Does that question make sense? Go find a painting, somebody long dead, right? And imagine that they made it today in Photoshop or something. It's still they're drawing, still they're still painting, but it's digital. It's not on a canvas anymore. Something you can print out. What's the difference? Would it be as beautiful? All right, that's my question. It's very open-ended. As long as you respond to the prompt, I'll give you credit. Write a 750-word essay along those lines. All right. I do want you to cite one source, please. So you're gonna have to include like a quote or a paraphrase in your writing, and like give me a citation and have a works cited page. I want you to cite at least one work, please. Okay. So here are some articles about this idea that you may want to read. They may help you as you're writing the essay, but you can find whichever one you like. That's most of the question. Are we still good with it? It's very, very open-ended. Okay, go find your favorite painting. Though there's some cool places to look for those. And if you are not really big on arts right now, that's okay. I'm going to force you to be a little bit, but like if you've never seen people doing crazy stuff with digital art, here's two people that I follow on Instagram as an example of like the two ends of like the spectrum that you could draw and you can paint with these days. Like here's a person that has a very cartoony kind of painting style, and it's all digital, which is really cool to think about. It's like it looks really nice, and I can't zoom in because I'm not logged in because Facebook wants to steal my data. But you kind of get the idea. There's that one, and then here's somebody who is like a concept art designer and virtually paints more realistic images. And so it still can look like something people have made in the past before digital stuff. So look into that. Look into the examples if you'd like. But yeah, I think that's pretty much everything. So a 750-word essay about like, would a digital painting version of an older painting still be as pretty to you? Questions about any of that? I think that's correctly explained. All right. So yeah, that's all that I got for us. Feel free to stick around and ask questions. Get started.